In the following video, we're going to discuss the loads on the bearings and the procedure for the bearing selecting. We can using the bearings equivalent loads to specify the design load for the bearing. For radial load, we can use the equation that say that the P is equal to the V multiplied by the R, where the R is the radial load and the V is rotation factor, which is going to be equal to 1 for the inner race if the inner race is rotate, or 1.2 if the outer race is rotates. So the procedure for the bearing selecting for the radial loads only is going to consist of the following points. First, specify the design load of the bearing. Usually it can be called the equivalent load, and the method of determining the equivalent load when only radial load R is going to be applied, going to take to the account whether the inner or the outer race is going to be rotated, which is going to be the same equation 14.5, that the P is equal to the V multiplied by the R. Second, determine the minimum acceptable diameter of the shaft that will limit the bore size of the bearing. Third, select the type of the bearings using table 14.1 as a guide. Fourth, specify the design life of the bearing using table 14.4. Fifth, determine the speed factor and the life factor if such tables are going to be available to select the type of the bearings we will use in the figure, using the figure 14.12. 6. Compute the required basic dynamic load rating, C, from the equation 14.1, 14.3, or the 14.4. 7. Identify the set of the candidate bearings that have the required basic dynamic load rating, C, and select the bearing that having the most convenient geometry and also considering the cost and the availability. 9th, determine the mounting conditions such as the shaft seal diameter and the tolerances, housing bore diameter and the tolerance, the means of lubricating on the bearing axillary, and the special needs such as the seal or shields. In our example on the bearing selection, we are going to have the case of selecting a single row deep groove ball bearings to carry the 2,891 Newton of pure radial load from a shaft that rotates at 62.82 radian per second. The design life is going to be 30,000 hours, and the bearing is to be mounted on a shaft with a minimum acceptable diameter of 37.59 millimeters. So the solution steps: first, the rotation factor V going to be takes the value of 1 if the inner race is going to be the bearing rotates, as the usual case. So use the 1.2 if the outer race is going to be rotates. So we start with using the V is equal to 1, and then the P value is going to be 2,891. Step 2, the minimum acceptable diameter is going to be 37.59 millimeters. In the third step, we're going to calculate the design life and the C value. We're going to use the same steps that we followed in the example 14.2. After we go to C value, we're going to go to the table 14.3, and we can choose the most suitable bearings that have the bore limits of 40 millimeters, which is more nearly in line with the desired shaft size. So in summary, we are going to list all the data for the selected bearings, including the bearing number, the bore, the outside diameter, the width, and the maximum fillet radius size. In most of the cases, we may have radial and thrust loads. So in that case, the equation will be expanded to be that the P is equal to the VXR plus YT, where P is the equivalent load, the V is rotation factor, the R is going to be applied radial load, the T is applied thrust load, the X is the radial factor, and the Y is the thrust factor. The radial and thrust factors for single row deep groove ball bearings is given in the table 14.5. So in the 14.5, you can see multiple parameters like the E, the T over CO, and the Y. The X and the Y will vary with the specific design of the bearings and with the magnitude of the thrust load relative to that load radially. For relatively small thrust loads, the X is going to be equal to 1 and the Y is going to be equal to 0 for pure radial loads. This presents the difficulty of the bearing selection because the value of the CO is not known until the bearing is going to be selected. Therefore, the simple trial and error method is going to be applied. So the procedure for the bearing selecting, if we're going to have radial load and thrust load, is going to be first by assuming the value for the Y from the table 14.5. The value usually is going to be considered to be 1.5 is very reasonable, being at about the middle of the range of the possible values. Then compute the P, which is equal to the VXR plus the YT. Third, compute the required basic dynamic load rating C from the equations 14.1, 14.3, or the 14.4. Select the candidate bearings having the values of the C at least equal to the required value. For the selected bearing, determine the CO. Compute the T over CO, and from the table 14.5, determine the value for the E. If Y ratio of the T over R is more than the E, then determine the Y from the table 14.5. 9. If the new value of the Y is going to be different from the assumed in the step number 1, repeat the process. But if the T over R is going to be less than the E, use the equation 14.5 to compute the value for the P and proceed for the pure radial load. So for the radial and thrust load, we're going to have the example 14.4 to select the bearing. So we need to select a single row deep groove ball bearings from the table 14.3 to carry a radial load of 8,228 Newton and a thrust load of 3,002 Newton. The shaft is to be rotated at 120 radian per second, and the design life is going to be 20,000 hours. It's going to be designed for our application. The minimum acceptable diameter for the shaft is going to be 78.74 millimeters. So the solution is steps. First, we're going to assume the Y is equal to 1.5 and the X to be 0.56. Calculate the P using the equation P is equal to the VXR plus YT. Use the figure 14.12 to find the value for the Fn and the Fl, and then calculate the C value. Now, using the C value calculated, and use the table 14.3 to select the bearing model that's based on the C value and the suitable bore for the application. For a selected bearings from table 14.3, we can locate the value for the CO. So the steps is going to be first using the value for the C that we have been calculated to select the suitable bearing number. After that, we are going to use the D to find which one is going to be the most suitable bearing according to the bore number. Third, we are going to find the static CO value for the basic load rating. With known CO, we can calculate the T over CO ratio. Go to table 14.5, find the value of the E based on the T over CO. If my value of the T over CO is not located in the second column, it's going to be actually possible to do the interpolation between the multiple values. Step number 8, if the T over R ratio is more than E, then we need to find Y. And once again, we can use the interpolation in the table 14.5 using the T over CO ratio. Now, we know the value. We can calculate the new P, which is equal to the VXR plus YT. Different is that we found a new value for the Y. Then we can calculate the C value. Once again, to go to step number 10, we need to choose a new bearing to replace the first one and repeat the steps from the step number 5. Well, step number 5, we need to find a new bearing and find the new CO, calculate the T over CO once again. Then we go to table 14.5 and find the value for the E. If my new T over R is less than the E, then the selection was satisfactory. If not, I will going to repeat the iteration once again. In this section, we're going to learn about the design and the selection of the tapered roller bearings. So you can see that in the tapered roller bearings, we can have both radial and thrust force that try to bend and push the shaft horizontally. Accordingly, the shape of the rollers is going to be used instead of the spherical shape. So it's not ball bearings, it's going to be roller bearing. For the tapered roller bearings, we're going to have two bearings, A and B. So we can have two equations to calculate the PA and the PB. The data of the tapered roller bearings is given in the table 14.7. So you can see that we are going to have different bore diameters, different outside diameters, the width, the A value, the thrust factor Y, and the dynamic load factor C. In the example 14.5, we're going to do the selection procedure for the tapered roller bearing. For a shaft that's shown in the figure 14.15 that carries a transverse load of 30,246 Newton and a thrust load of 11,120 Newton. The thrust is resisted by the bearing A, and the shaft rotates at 36.64 radian per second and is to be used for the piece of the agricultural equipment. We need to specify the suitable tapered roller bearing for this shaft. So first, the radial load of the bearings can be calculated as following. We can find the resistance at the bearing A and the resistance at the bearing B, while the thrust load at the bearing A is equal to the 11,120 Newton that's already been given in the question. The next step is to assume the values for the YA and the YB as 1.75 and use the equation 14.8. Now we apply the equation 14.8 to find the value for the PA, and the PB is going to be equal to the radial force for the bearing B. Now select the 4,000 as the design life, and we can calculate the design life by using the equation of the number of the hours multiplied by the RPM multiplied by the 60 minutes divided by hour to get how many revolutions that this shaft will be running through. Then use the equation 14.3 to get the basic dynamic load rating for the bearings A and B. Now from the table 14.7, we can choose for the bearing A both the bore diameter D small and the outside diameter D capital. Also, we can find the value for the C and the value for the YA. We can repeat the same thing for the bearing B. Next step is going to be recompute the equivalent loads PA and the PB. Now, one caution must be observed in the using of the equations for the equivalent loads for the tapered roller bearings. If from the equation 14.8, the equivalent load of the bearing A is going to be less than the one applied radial load, then the following equation should be used instead. If the P over PA is less than the reaction force at the bearing A, then we let the PA is equal to FRA and then compute the PB as following. The PB is going to use the same equation that we used earlier for the PA and vice versa.